So hello everyone, this is the advanced section on quantum complexity theory by Avantika for the mini course on computation. Yeah, so maybe Avantika, you can start with introducing yourself and the topic, and it's your stage now.
Okay, so hello everyone, I am Avantika Agarwal. I am a third-year undergraduate student in the computer science department at IIT Delhi. So my primary interest is theoretical computer science, and I have been looking in quantum complexity theory for some time now, like for the past semester. Today, I would be talking about quantum complexity theory, although like not exactly the quantum complexity classes. Instead, we would be talking about a particular method for lower bounding the difficulty of some problem. So like in the previous talk, we saw Grover's algorithm, which provides a polynomial speedup over the time required to solve the search problem classically. But today we are going to question whether that is really the best we can do. So is it possible like Grover's algorithm works in like O root n time? So is it possible that we are able to do something like O log n or O log square n time to search for a 1 in our unstructured database? Today we are going to like pose that question, and we'll see that whether or not it is possible. We are going to look at a particular technique for proving that it is actually not possible, and that n raised to power half is basically the best we can do. Well, I have been talking a bit informally, but yeah, I'll formalize the content of my talk now. So before I begin, I just wanted to introduce some background. Although I think almost all of the attendees were present in the previous talk too. So this part is hopefully going to be easy. So I'll be talking about the black box model of quantum computation. It is actually like a classical model too. We just extend it to the quantum setting. So our aim is that we want to decide a language. So we want to compute some function on an n-bit input, which gives us a single bit output. For example, we might want to like have an n-bit input, some 0, 1, 0, 1, and we might want to output a 1 if this string contains at least a single 1, and we might want to output 0 if the string is all zeros. So basically, we are deciding a language on an n-bit input string. And the way we are given access to this input string is that we can query the bits of this input string. So what does like querying the bits of an input string mean? So we have an n-bit string x. Suppose this, and by querying a bit of this input means our machine can ask some black box, okay, tell me the third bit of this input. And the black box would tell us that the third bit is 0. Then the machine could ask, okay, tell me the fifth bit of this input, and the black box would tell us that the fifth bit is 1. And the machine can make as many queries on this input as much as it wants before concluding what the value of fx is. So ideally, we would like that we make as few queries as possible, because that would make our algorithm for computing f efficient. So like I told you, in the classical setting, there would be, so we'll query the ith bit and we'll get the ith bit in the output. In the quantum setting, however, the queries work a little bit differently. So like we saw in the previous talk that we can create superposition of states in a quantum computer. So here in the quantum setting, if we want to query something, we can actually make superposition queries to our black box. So we can actually make a query like this. So if we query, say, get I, then we would then our output from the black box would be minus 1 raised to power xi times I. So if xi is 1, then the phase of our input is flipped. If xi is 1, then we would be getting minus I, minus ket I. And if xi is 0, then we would be getting ket I. So in a way, the output of the black box is like contained in the phase of our input. And like I said, we can make superposition queries to the black box. So we can make a query like this: I plus get j plus get k by root 3. And the output would be -1 raised to power xi get I plus -1 raised to power xj get j plus -1 raised to power xk get k by root 3. Does that make sense, like how a superposition query to the black box is working? Should I take that as a positive?
Okay, so maybe I'll make some reactions. Yes, I think it's quite clear. Yeah, and if no, people please feel free to speak in the chat.
Okay. So let us see how actually such a query algorithm could work. So suppose we are given query, we have this black box for this input string x, and like I am this Bob, and I want to decide this OR of n problem. So OR of n problem is that we want to output 1 if the string contains at least a single one. Otherwise, we want to output 0. So what I would do is I will make like, I'll first query the first bit. So let us say these are the n bits of my input. And right now, I don't know what the n bits are. So I'll query the first bit of my input. Suppose it comes out to be 0. Then I query the second bit of my input. It again comes out to be 0. Okay, I'm talking in the classical setting. I first query the first bit of my input. It comes out to be 0. Then I query the second bit of my input. It again comes out to be 0. And I keep querying until I query some bit and I get a 1. As soon as I get a 1, I can output 1 because now I know that this string contains at least a single one. While I'm not getting any one, I would have to keep querying to make sure that like a 1 is not present in the part of the input that I have saved. So like in the worst case, we can see that a classical algorithm would be making n queries to this black box before it can give us an output. This is exactly what the Grover search problem was. So like in the classical setting, we need to make at least n queries to be able to give the correct output on all inputs. And what Soumya talked about was, so this Grover's algorithm, using which we can give this output in like O root n queries. And today we are going to question whether that is really the best that we can do, or whether or not like we can improve this. So whether we can get O log n queries, suppose. We are going to look at a technique that using which we can analyze whether we can do something like this. So before we go further, I would just like to define these quantities formally, what it means to make n queries or O root n queries. So this is just like 3 quantities that I want to define formally. So first is like, okay, I'll maybe only define 2 of these. So the first is deterministic query complexity, D of f. So D of f is basically refers to the minimum number of queries that an algorithm needs to make to compute the function f for all inputs x. Okay, maybe I should say that more slowly. Okay, so D of f is minimum number of queries that a classical algorithm needs to make to determine fx for any x. So like a classical algorithm might need just 2 queries for one particular input, and it might need like 10 queries for another input. So supposing that 10 is the maximum number of queries it needs over all the inputs, so we'll say that the classical query complexity is classical deterministic query complexity is 10, like for 10-bit inputs. Does that make sense, or did I not explain it properly?
I think it's clear to me.
But yeah, I think I can do a better job. Yeah, I should do a better job.
Other people?
Yeah.
Can you hear me?
Yes.
Hello. So
Yes, I can
yeah,
hear.
so that means if the n is 10, if let us say that n is 10,
Yes.
that means the minimum number can be 1 itself, right? We can, the first query itself can return a 1. So d of
Yes.
s
So
should be 1, right?
we will say that d of f is 1 if it can output the value of fx for any x in a single query. So it could be possible. So let's take the example of or of n. So for this let us say n equals 4. So for this particular string, if I just query the first bit, I'll be able to output a 1. But for this string, I will need to query each of these bits before I'm able to conclude that, okay, there is really no 1 in this string. And hence I should output a 0.
Oh, is this the analog of a classical worst case complexity? That's the same, right? Like the worst case complexity for any algorithm in the classical sense.
Yes,
That
yes.
is the same as this.
Yes. So actually, like, this is a particular computational model. We call it the decision tree model. So this is just the worst case complexity in the decision tree model.
Yeah, just as a side note, like, can we apply merge sort or something like that, those kind of algorithms to this, or is it completely different paradigm that we can't apply that? Just a
Actually,
small
like,
curiosity of mine.
yeah. So like in this decision tree model, we actually don't really know what our input is. So like in the merge sort case, actually,
Oh,
in the
I
merge
understand. I understand. The in merge sort or anything, the array is already given, like the values are
yes,
already determined, but here we
yes,
can't. Hmm.
yes. So like
Okay, okay.
in the merge sort case, like our starting point would be different for each input. And here in the decision tree case, our starting point is always the same. Like our algorithm starts differing after we make a few queries. Because like initially we don't really know anything. We just know that we want to compute this function.
Interesting, interesting. Yeah.
So if the deterministic query complexity makes sense, then the next query measure that we would like to define is QF, which is basically the quantum analog of this deterministic query complexity. So here again, the minimum number of queries that a quantum algorithm needs to make to determine fx for any x. So
sorry to interrupt. Can I ask one question?
yes, definitely.
In this query model, like you are querying, so for like your ith query is bit xi, but suppose like if the query is like the query can take two inputs I and j, and it will output the maybe and of xi and xj.
No, actually, that's not how we work in this model. So that would be a different oracle altogether.
Right. So, like my question was like, I understand that this is the like simplest model which we should look upon, but does things like really change when we take different models, or
So actually, like
different
for the
different oracles? I mean.
yeah. So for the particular case that you are suggesting, where like we just input ij and we get xi and xj, I don't think it would really make a difference, because like we are only increasing the number of so like we can in this if we are querying like xi and xj, we are only like increasing the amount of information that we get from a single query by like a constant amount. So I don't think in this particular case it would matter, but in general you can like come up with some very complicated things. So like you can take the halting oracle and just ask it whether this particular Turing machine would halt on input X or not. And if in that case, it would make a difference. So in general, yes, it makes a difference. But for this particular Xi and Xj case, I don't think it should make a difference. So like the query complexity would at most differ by a constant in this case. But in general, you can do very strange things if you allow for like any kind of oracle.
Thank you.
Did I get that right, Chi-Ning, like the halting thing? I think we can get the arithmetic hierarchy that way.
Yes, I think it makes sense. Yeah. Yeah,
Okay.
and maybe for query model, if people are interested in, I can maybe in the end provide more like motivations and a high level picture, yeah, and connection to other stuff. Yeah, but here maybe, yeah, indeed you can just think of it as, okay, I want to compute the Boolean function, but the input, I cannot see the whole input. I can just access certain bits. Yeah, but I allow you to access it with different weights, and deterministically you can only access one bit at a time, and quantumly you can have a quantum query, something like this.
Yes, thank you. So, okay, this QF is the minimum number of quantum queries that an algorithm would need to make to determine fx. So like I would just to like make it very clear. So in the quantum setting, if I am making a query like this, a ket I plus ket j plus ket k by √3, this would only count as a single query and not as 3 queries because we are making it in superposition. So if I had made these 3 queries separately in succession on a quantum oracle, then it would have counted as 3 queries. But so long as I'm making it in superposition, it only counts as a single query. Like it is my problem how I come up with this superposition. But to the oracle, it will only count as a single query. So I hope the definition of DF and QF is clear. And like just for example's sake, I just showed that like for OR of n, the D of OR of n is basically n. So we, in the worst case, we'll need to query all of the bits of the input before being able to output something. And Q of OR of n, we saw in the last talk that it is O√n. And today we want to see whether it is also omega√n or not. So I hope everyone is clear with like big O and big omega notations. Well, if you're not, just like big O is an upper bound and big omega is a lower bound. That's all you need to know for this talk. So yeah, today we are going to ask whether this is the case or not. So for this, actually there are multiple methods in literature that we can use to lower bound the query complexity. So like I'm just going to list some of them. So there is this hybrid method. I think this was the first method that lower bounded the complexity of Grover's algorithm. This was by BV in, I don't know, some 90s, I think. Then there is this adversary method. So it has like 2 formulations, this positive adversary method and negative adversary method. And this method is actually quite strong. So there is something called Ricardett's theorem, if you're interested, which says that like the adversary complexity is like theta of the query complexity. So yeah, you don't need to pay attention to that if you're not familiar with these terms. And thirdly, there is this polynomial method. So this is actually a very simple method and mostly requires just our high school mathematics. So I'll be talking about this method. I really like it a lot due to simplicity. So yeah, so the polynomial method says the following. So it has basically 3 parts. Firstly, it says that we can represent a function as a polynomial. So I'll tell you what it means like in a few minutes. Right now, I'm just summarizing what we are hoping to achieve through this method. So firstly, that we can represent each function, each Boolean function that we want to compute as a polynomial. Secondly, I'll prove that the query complexity of each function is lower bounded by the degree of a polynomial. So I'm going to prove that, okay, what did I do? Yeah, so I'm going to prove that if we want to compute some function f, then the query complexity of this function is lower bounded by the degree of some polynomial p. So this polynomial is basically the one we are talking about in the first step. Then we are going to say that the query complexity is actually lower bounded by the degree of this polynomial. And like once we have done this, then it is clear that our third step would be to lower bound this degree of this polynomial p. Because so long as we have shown that this degree of p is greater than something, then we have shown a lower bound on the query complexity. So actually, like if you look at it on a high level, we only need to establish this part 1 and 2 because we have done a lot of lower bounding degree of polynomials in high school itself. So like that is the comfortable area. We don't really need to worry about that too much. That is just algebra. And I'll be talking about these two parts first and then just give an example for the third part. So I hope like the broad plan is clear. I'll be first representing a function as a polynomial. Then I'll be showing that the query complexity of that function will be lower bounded by the degree of this polynomial. And then I will be lower bounding the degree of the polynomial itself. Okay, so how do we represent a function by a polynomial? So there are actually two ways of doing it. So suppose we have a function from n bit inputs to a single bit output, then and let x be our input. So a polynomial exactly represents a function f if, so let x be x1, x2, xn. So a polynomial will take this x1, x2, x3, xn as input. And it exactly represents a function f if p of this x1, x2, xn is equal to fx for all x. So like computing the function is basically equivalent to computing this polynomial if we know what this polynomial is. And a polynomial approximates a function f to like, so if we are approximating, so there must be some error. So let us say that our error is 1/3. Then a polynomial p approximates f if p of x minus f of x is bounded by 1/3. So it is like, it might be different from f, but it won't be like way off. It will be very close to what the value of fx is. So I hope these two ways of representation are clear and like make sense why we would do something like this. Should I move forward or like, does anyone have any questions?
So just to clarify, so the polynomial work over reals and the guarantee is for the x.
Yes, yes. So yeah, this is a real polynomial. We'll see it later also. But yes, this is a polynomial over reals. And in the exact case, its value will be equal to the value of fx for all x. Although yes, like since these x1, x2, xn can actually be integers in general. So like for inputs other than these n-bit inputs, the output of this polynomial could be anything. We don't really know what the output of this polynomial would be. So yeah, it will only agree with the function on these particular n-bit inputs x. And for the, so like, I would just like to point out here for, yeah, just to keep things clear that this polynomial in general can be assumed to be multilinear. So because like suppose this polynomial p x1 comma x2 is something like x1 square plus x1 x2 something plus 1 minus x1. So in general, because this x1 x2, we only care about the value of this polynomial at like n bit inputs. So like x1 x2 x3 xn, all of those would always be either 0 or 1 when we care about the value of this polynomial. So in general, we can replace this x1 square by x1 and the value would remain same because 0 square equals 0 and 1 square equals 1. So this so like the highest power of any of these variables in this polynomial would always be 1. So it will be a multilinear polynomial in general. And like given these two ways of representation, now we can define two quantities. So like earlier I talked about the query complexity being lower bounded by the degree. So now I'm going to talk about what this degree exactly is. So there is this exact degree and there is this approximate degree called degree tilde. So this is the exact degree and this is the approximate degree. So exact degree is minimum degree of polynomial, which exactly represents f. So there could be like multiple polynomials, p1, p2, p3, pk, all of which are equal to fx for like all inputs x. So we just take all of these polynomials and suppose the minimum degree among all of these is some pi, which has degree, say, 3. Then in that case, the exact degree of f would be 3. So we take all of the polynomials which represent f and we pick up the minimum degree among all of those. So that is the exact degree of f. And for the approximate degree, again, it is the minimum degree of polynomial which approximates f. So in the exact degree, the polynomial was exactly representing f. In the approximate degree case, the polynomial approximates f. So we take some p1, p2, pn, all of the polynomials which approximate f, and we pick up the minimum degree among all of those. So that would be the approximate degree of f. Is that okay?
Yeah, it's quite clear to me. It is. Yeah.
Okay. Yeah, so I think we have established the first part, like we had 3 goals here. So I think we have established this part that we can actually like how we can represent a function as a polynomial. There are 2 ways. First, we can do an exact representation. Second, we can do an approximation to some error. In our case, we have assumed that the error is 1/3. And now we want to move to the second part where we say that, okay, now we can represent a function as a polynomial, but how is that useful? So we'll say that the query complexity of computing this function is actually lower bounded by the degree of this polynomial. So like the result I'm hoping to establish is like these. So maybe just ignore this RF1 because I didn't introduce it. Yeah. So the first result is that the quantum query complexity is lower bounded by the approximate degree divided by 2. And the classical deterministic query complexity is lower bounded by the exact degree. So like, I hope it makes sense why it is approximate degree in the quantum setting and exact degree in the classical setting. So basically in the DF case, we were outputting like the correct answer always. So this was the deterministic case. And in the deterministic case, if we're calculating a function, then we are obviously always calculating the correct answer. So in this case, we would be talking about, it makes more sense to talk about a polynomial which exactly represents f. And hence, like I'm just trying to give you some intuition why this is approximate and this is exact degree. So in the deterministic case, it would be exact degree of f. And in the quantum case, we have seen in the previous talk that quantum computers are inherently probabilistic. So there always some success probability. So if we like at the end, if we measure our circuit, so there is always some probability of getting 1 and some probability of getting 0. And so like they're inherently probabilistic is in nature. So like there is a chance of us making some error with some probability in a quantum computation. So that's why in this setting, it makes more sense that we are talking about an approximation to F. And hence here the degree would be lower bounded by the approximate degree of F. So like I'll prove this formally. I'll only prove this one part formally. The second is actually much simpler. So I won't be talking about this. I'll only be proving the first part. And I think this is the only formal proof I'm going to do. Just to keep things, just to like convey the main ideas and not get into too much details. So we are hoping to establish that QF is lower bounded by degree of F by 2. So to establish this proof, like let us first look at what in general a quantum query algorithm could be doing. So suppose again, I am Bob and I want to compute some function F. So I will like first make a query. Let us represent our queries by O. And in general, any other gate that we apply to our circuit, any other unitary gate, we saw in the last talk that the gates are unitary. So that we'll represent by some U. So in general, what I would be doing to compute F is I'll make a query. Then I'll do some computation on my own through these unitary gates. Then I'll again make a query. Then I'll again be doing some computation. Then I'll probably again make a query. Then again, I'll be doing some computation and so on till I make my last query. Then I again do some computation. Then I do a measurement. And then I output whether my answer is 0 or not. So suppose suppose I'm making T queries in this algorithm. So I am saying that this T is lower bounded by the approximate degree of F upon 2. This is what I'm hoping to prove. But I hope the setting is clear, like what I would be doing. So yeah, let us look at it like somewhat more mathematically. So in the beginning, I would have some psi initial state. It would be some sigma or I, alpha I, ket I. Whatever, this is my psi initial normalized state before I have made any kind of queries. So all of these alpha i's would be some constants. Right, then I make my first query. So I make this query. So my state would be alpha I minus 1 raised to power xi ket I. Is this part clear? Like we saw how queries are done previously. So I'm making a superposition query and I'm getting a superposition output where my query is stored in the phase. Now, if you like look at it carefully, suppose xi is equal to 1, then this is actually minus alpha I ket I. And if xi is equal to 0, then this is alpha I ket I. So I can actually write this as sigma alpha I Oh, I should have introduced this thing first. Okay. So yeah, like just a digression, I actually forgot to introduce something. So I said that if I make a quantum query, I'll give an input I and I'll get something like this, minus 1 raised to pi xi followed by ket I. This is actually equivalent to another oracle query. So I give this input I and I give some single bit B to the oracle as input and I get I with B XOR Xi in the second qubit. This is basically equivalent to this query model. Both of one can simulate the other, that kind of thing. So I hope this makes sense. This is also a very valid way of making a query. So if I set this B to 0, then so if I input I 0, then I'll be getting I Xi. And if I input I 1, then I'll be getting I 1 XOR Xi. So 1 XOR Xi is basically equal to Xi complement. So this is also an equivalent query mode. So maybe just look at that for now. In that setting, if you look at this part carefully, so what I have done is, if I make this query, I, B, then I would be getting I, B XOR Xi, right? And if Xi is equal to 0, then that would mean I got IB. And if Xi is equal to 1, then that would mean that I got I 1 minus B. Because I would be XORing B with 1. So I 1 minus B. Yeah, I'm sorry I did not introduce this earlier, but I hope this makes sense how this query is working. So if anyone has any questions, they can ask.
So I think, yeah, you define it quite mathematically quite nice. And just for people, if you want to take a step back to look at the definition, you can think of, as I mentioned in the chat, this is just some way to guarantee the unitary property of the operations. Yeah, because in quantum, every operation is unitary. So that's why we cannot do like query did in a Turing machine. We query and get an answer. Yeah, the answer should also be lying in some form in the original state. Yeah, so we have an extra register for it, and then it is just a XOR on it to make sure the operation is invertible.
Yes, I should have said that actually. Thank you.
No problem.
Thank you. So yes, so once we see this, then it is not very hard to see that if I'm making this IB query, then in general I can write my output as Xi times I times 1 minus B, Xi tensor I tensor 1 minus B, plus 1 minus Xi times I tensor B. Why is this correct? Because suppose Xi is 0, then this part is 0, and basically I am getting IB, which should be the output. And suppose Xi is 1, then this part becomes 0, and I am getting I 1 minus B as output, which I should be getting. So in general, we can write any query this way, right? If this makes sense, then it should be clear that the query that we made earlier, this can actually be written as alpha I times Xi I 1 minus B plus 1 minus Xi IB. Yeah, I hope this makes sense. So basically what we can see is now our state, so earlier all of our amplitudes were constants. And now the amplitude has actually become a polynomial in all of these Xi's, a polynomial of degree 1 in all of these Xi's. So yeah, I hope that is clear. It is very difficult if I cannot see people's faces and just have to guess. So yeah, so what we are seeing is I made this first query to the oracle, and the amplitudes become a polynomial of degree 1. And so next I will be doing some unitary computation. And because this computation is unitary, the degree of this polynomial in the amplitudes, this won't actually change. So it can be proven mathematically if you spend some time, but I won't be doing here for the sake of time. I don't have a lot of time. So yeah, let's just assume that a unitary computation will not change the degree of this polynomial. So if it was a degree 1 polynomial, the amplitudes were a degree 1 polynomial before the unitary computation, then they would remain a degree 1 polynomial after the unitary computation too. So again, this is some I alpha I xi something, some degree 1 polynomial. And then I again make an oracle query. So this is my second query. Then again, I would be in a similar manner, I would be adding another xi here. So like my polynomial, which was earlier degree 1 polynomial, it would now become a degree 2 polynomial. So the amplitudes will now become degree 2 polynomials. So I will get something like alpha I xi xj j1 minus b plus alpha I xi 1 minus xj jb and so on. So these would be like, now the amplitudes are degree 2 polynomials in the input grids, and so on till the tth query that we make. So like by induction, now we can say that after the tth query, each of these polynomials, so let's say we make t queries, and this is our state after the t queries. Then we would have this sigma over I sum p x1 to xn I. This would be our final state, suppose. Then by induction, we can establish that each of these pi's, this would be a degree t polynomial, at most degree t polynomial. Because in each query, we are increasing the degree of this polynomial by at most 1. So we have shown that these amplitudes are degree t polynomials. And the final step of our computation, like any other quantum algorithm, would be making a measurement. So once I make a measurement, my probability of measuring any of these, so like if I make a measurement, I would be measuring one of these i's, ket i's, and the probability of making that measurement would be mod pi square. So because like in general, if we have alpha 0 plus beta 1 kind of state, then the probability of measuring 0 is mod alpha square, probability of measuring 1 is mod beta square. So here, if I'm measuring I, then the probability of measuring I would be mod pi square. And since we are doing mod, so like this gives us two things. First, since we are doing mod, so the final polynomial that represents our function f, that would be a real polynomial. Secondly, the degree of this mod pi square would be like double the degree of pi at most. So we have basically established that there exists some polynomial p such that firstly that px approximates fx. So like because firstly that px approximates fx because this px basically represents our probability of giving the correct answer. And secondly, that this px is a real polynomial. Real polynomial of degree less than equal to 2t. Because like the degree of pi was t, so this degree of p mod x square would be less than equal to 2t. Does this part of the proof make sense? Okay. So like by doing this much, we have shown that there exists a polynomial which has degree less than equal to 2t and approximates f. And by the definition of approximate degree, we know that the approximate degree of f must be less than equal to this degree, because we have already shown that there is a polynomial of this much degree which approximates f. So the minimum degree of polynomial approximating f must be less than equal to this degree. So we have shown that approximate degree of f is less than equal to 2t. And like this gives us the claim that we initially wanted to prove, that t is greater than equal to approximate degree of f by 2. And t is equal to qf because t is the number of queries I made, or like number of queries Bob made. So qf is greater than equal to approximate degree of f by 2. So like, is this claim clear? Because this was basically the main idea for polynomial method. So if you take away nothing else from this talk, maybe just take away this claim. So yeah, if anyone has any questions, they can ask. Shall I move on?
Yeah, and also you probably don't have too much time left, say like 5 minutes. Yeah, so you can see how to adjust the time.
Yes. So okay, we have established that the query complexity is lower bounded by the degree of such a polynomial. And now we are in the easy domain, right? So we know that the query complexity is lower bounded by the degree of polynomial. Now we just want to like lower bound the degree of this polynomial itself. That is like high school mathematics. We have done it a lot of times. So that should be the easier part. Now we just want to lower bound. So we suppose I show that this degree is lower bounded by some c, then I have given a lower bound on the query complexity. The aim is just to find a good lower bound on the degree of the polynomial. So in the interest of time, I'll first do an easy example, then I'll move to a more difficult example, somewhat more difficult example. So like in general, any method that you can think of which lower bounds the degree of polynomial representing a function f, that is a good enough method. Like, you're done, you have given a lower bound. But in particular, I want to like talk about like this particular technique called symmetrization. So I have shown the existence of this polynomial, some p x1 x2 xn, a multilinear polynomial. But like in general, like lower bounding the degree of a multilinear polynomial could be difficult. So we use this particular technique called symmetrization and try to make our life easier using this technique. So what we do is we symmetrize this polynomial for inputs satisfying a particular property. So what I'll do is, let us say I pick up the property Hamming weight. So my aim is I create this polynomial p prime from this polynomial p, which again takes x1, x2, xn as input. And the value of p prime is same for all inputs which have the same Hamming weight. So what I'll do is, so I'll take the average of all inputs with same Hamming weight. So suppose this input has Hamming weight 2, then the value of p prime for this input would be the average of px on all inputs with Hamming weight 2. So p of 0, 1, 0, 1 plus p of 0, 1, 1, 0 plus so on, all inputs with Hamming weight 2 upon whatever this number of inputs is, some c. So that way we have ensured that like all the inputs which have the same Hamming weight give the same output for this polynomial. Now that makes our life a little bit easier because this polynomial is now easier to think about. We don't have to worry about that 0, 1, 0, 1 and 0, 1, 1, 0 will have different outputs. So like multiple inputs have now same outputs. And since this polynomial is now only dependent on the Hamming weight of the input, we can further simplify it. Again, this can be proven mathematically. I'm not doing it in the interest of time. So I can further, using this p prime, I can create this polynomial qt, where t is the Hamming weight of input. So like now the output of this qt is same as p prime x1, x2, xn. But since anyway, the output of p prime was just dependent on the Hamming weight, all input strings with the same Hamming weight at same output. So I can create another polynomial qt, which just takes the Hamming weight as input and outputs this value of p. And I can show actually that this degree of Q is less than equal to the degree of P prime, and is less than, which is in turn less than equal to the degree of this original P that we found from our construction, which was less than equal to 2T. So again, now we are just trying to make our life simpler. If I am able to give a lower bound for this polynomial Q, some C, then I have effectively given a lower bound for our query complexity. I hope that makes sense. Like if anyone has any questions, they can ask. Okay. So I'll just move on. I'll first do a simpler problem.
Avantika,
Yeah.
we cannot hear you so well. There seems to be some connection problem.
Oh, I see. I see. Just give me 2 minutes. I'll correct. Can you hear me properly now? I have changed my internet connection.
Yes, yeah, and also since now it's already 11:52, maybe here in Eastern time, so maybe you can maybe use
I'm
1 minute to
just
wrap up and give a summary, and you can talk more if people are interested to hear.
Yeah. Okay. Okay. So like we did 3, I'll first just summarize and we can talk about this maybe later. So the aim of the polynomial method is the following. First, we represent a function as a polynomial. Then we say that the query complexity of this function is lower bounded by the degree of this polynomial. So this we have actually proven. We don't need to do it again and again. We just need to do this first part. We need to figure out like how to represent a function as a polynomial. And then we go directly to this third step where we lower bound the degree of this polynomial. Any method that we know which can lower bound the degree of a polynomial is good enough. We just need a lower bound, and like there is no hard and fast rule like you have to lower bound the degree this way or that way. So yeah, we just need to lower bound the degree of the polynomial. This is like, in summary, this is the polynomial method. And like to give a particular example, let us look at this exact or-in problem because it is a simple example. So in the or-in case, we saw that classically we need n queries. In the quantum setting, we saw that the Grover's algorithm needs O root n queries. But there is actually this caveat that quantum computers are inherently probabilistic. So this Grover's algorithm has some small probability, some epsilon probability of error. So like it's like we trade off our deterministic success for this small error probability, and in turn get this polynomial advantage of query complexity. So now I'm asking the following question, like, is it possible for a quantum computer to calculate or-n exactly in O root n queries, suppose? So like here we make, in the Grover's algorithm, we make some epsilon errors. So can we do this exactly using a quantum computer? And it turns out that the answer is no. Why? Because we saw that there is this polynomial P, which represents our exact or-in function. And from that, we can create this polynomial P prime by symmetrization. So this polynomial P prime we can create using symmetrizations, which has the same output on all inputs of same Hamming weight. And from that, we can create this polynomial Q. which just takes in the Hamming weight as input and gives us some output. So what I'm saying is, like, let us just consider directly this polynomial Q. And what do we know about this polynomial? We know that the output of this polynomial Q on input 0 would be 0, because Q is exactly representing F. So now, since we are talking about the exact OR case, we need a polynomial that exactly represents F. So like Q of X would be equal to Fx. P of X would be equal to Fx for all X. So Q of 0 is 0. And Q of 1 is 1, because like Hamming weight is 1, so there must be at least a single 1 in the string. And Q of 2 is 1, and so on for all of the n bits. Q of n is 1. Yeah, I hope that is clear why that is the case, because this Q is also representing F, just like this P did. So Q of 0 is 0, and Q of 1, 2, 3, all n integers is 1. But like this gives us something interesting, right? So suppose this is our axis, coordinate axis. So for 0, this Q is 0. Then for 1, this Q is 1. For 2, this Q is 1. For 3, this Q is 1. And so on. For n, this Q is 1. Let us define a polynomial Q prime. So Q prime of t is equal to Qt minus 1. So that would be something like, for 0, it is minus 1. For 1, it is 0. For 2, it is 0. And so on. For n, it is also like 0. And what does that tell us? That tells us that the degree of Q prime, this is greater than equal to n, because we have already shown that it has n zeros. And the degree of Q prime is equal to the degree of Q, because we just subtracted a 1 from Q to get Q prime. And this degree of Q is upper bounded by 2 times T. So we have effectively shown that the query complexity of exact OR is greater than equal to n by 2. So it turns out indeed that we cannot compute this OR function exactly on a quantum computer either, using O root n queries. So yeah, this gives us a concrete non-trivial lower bound on the query complexity of exact OR function. So like just as a fact, because that was the initial motivation for this talk. In general, for the OR function also, it turns out that we have an omega root n lower bound. So the Grover's algorithm is actually the best that we can do to calculate this OR function, even approximately. We cannot do something like O log n. So it can be proven again simply using like lower bounding the degree of polynomial techniques, but I'm not doing here in the interest of time. So yeah, I hope that made sense, and sorry for going over time. If anyone has any questions, they can ask.
Yeah, so sorry for the noise, yeah, on my side, but maybe let's thanks Avantika for the talk. So maybe given the time is a little bit late, maybe let me stop recording now and people can ask questions.